Hi everyone. All right, this is our video where we're going to go over k-nearest neighbor, and I'm going to give you some sort of background information about this particular classification process. These slides actually are, instead of me creating new slides, I took these directly from the textbook website. There's a slide set for every chapter in the textbook, and I modified them a little bit to drop some of the stuff that I don't really want to cover. But anyway, these are right from the textbook. So, characteristics of kNN. It is data-driven, not model-driven. What does that mean? In the past couple weeks, we have created models, one for linear regression and the other one for multiple variable linear regression. And those are models that we had to actually submit to the R function and have the R function return back an intercept and coefficients that we could then build a model with. Well, we don't have to do that with kNN. What kNN does is it looks at the data and it looks at the records that we want to classify and it compares them. And it says, okay, the data that we know about fall into these classes. So there's maybe a class A, a class B, maybe even a class C. And each one of these records has a class that is assigned to it. So we're just going to look at that data and we're going to check that data when we also look at new records. We bring in new records. We haven't determined if they're class A, class B, or class C. We're going to look at the values of variables in the new data, compare those values to variables in the classified data, and then determine the class of the new records. So it is not model-driven. We don't have to build a model. We will not finish this process with a built model. And each time we run the kNN classifier, we will re-examine the comparison of new records to be classified to all the other classified records already in the data set. Basic idea: for a given record to be classified, what we do is we identify nearby records. Now, what does that mean? Nearby records are determined by the specific values that we pick. So we may have records that have maybe 15 different variables, and we're not going to look at all 15 of those variables. There may be only 2 or 3 variables that are actually even useful or interesting to us. So we're only going to look at those. So we're going to compare the new records. Let's just say it's 2 variables. We'll look at the 2 variables in the new records and we'll compare it to those same 2 variables in all of the classified records. What we're going to do is we're going to determine which records are closest. Now, how many records are we going to look for? How many close records are we going to look for? That's what K is. K is a user-defined variable. It can be 1, it can be 5, it can be whatever. And there are entire algorithms to help you determine what K should be. In this presentation, we'll talk about the dangers of picking a K that's too small and the dangers of picking a K that's too big. But anyway, the idea is that you pick K. And let's just say, for example, it's 3. So what we're going to do is we're going to look in our classified data set. We're going to look for the 3 records that are closest to each of the records that we want to classify, each of our new records. When we do that, we're going to determine what class the classified records are in, and the record to be classified is going to take on that particular attribute, depending on which one it's closest to. So near means records with similar predictive values. Those would be x1, x2, xp. And then we're going to classify the record as whatever the predominant class is amongst the nearby records. The idea is that if you pick an odd number for k, in our case we picked 3, and you have 2 of the records that are closest belonging to class A, and the third one belonging to class B, the the record that is new, the record to be classified, is actually going to be dropped into class A because 2 of the closest records are in class A, 2 out of 3, and it's the majority that takes dominance. How do we measure nearby? There are multiple ways of measuring this, and they fall into different categories. The textbook goes through some of them. We're not going to worry about getting into the weeds of doing calculating nearby. We'll just talk about Euclidean distance. Euclidean distance is the most common, and it is basically where we take the 2 variables. There's 2 variables in every one of our classified records and 2 variables in every one of our records to be classified that we're interested in comparing. And so what we'll do, we'll take variable 1 in the record that's classified, and we'll subtract from it variable 1 in the record to be classified. Then we'll take the difference between those two and we'll square it to get rid of any negative numbers, and we'll add it to the second variable, the difference of the second variable between the classified record and the record to be classified. Again, squaring that so that we can get rid of any negatives. We add all those up and we take the square root to get rid of the square, and we come up with a distance. This is really very common to like root mean square or something, some statistical variables that we use. But what it really is it's calculating the distance by doing the difference between the variables. When it does that, it does it actually for every single record in the classified sets. So you take on a new record and you compare it to every record in the classified sets, and then you just basically find the smallest ones, the ones that have the smallest distance. In R, there's a couple different ways we can do this. The first thing we have to do in R, and this is getting onto the bullet points on the slide, the first thing we have to do to R is we have to standardize or normalize our data. And that's a whole new thing we've not had to deal with before. When we standardize or normalize our data, what we're basically doing is we're converting the data to be all on the same scale. And there's a reason for doing that. If, in our example, we have variable A and variable B, if variable A, the range of variable A runs from, say, 1 to 10, it's going to be very different than variable B, where variable B might run from 1 to 100. When you actually calculate your Euclidean distance, you can tell that if variable B runs from 1 to 100, it's going to take far more weight in determining the distance between the data points. Even though the scale really shouldn't give it that much more weight, it does take far more weight. So what we want to do is we want to reduce the scale of 1 to 10 and the scale of 1 to 100 down to a common scale. And there are a number of ways to do this as well. The way that the book does it and the way that our example does it today is we convert to z-score. If you remember from statistics, the z-score is basically the number of standard deviations from the mean. So you calculate the mean, you subtract the value from it, you divide it by the standard deviation. That's done using a function in R called preprocess. And we'll have to download a package in order to make that work. But preprocess will allow us to build a template or build a model that converts everything to z-score. And so we'll do that in the script, and I'll show you how we do that in the script. And then we'll actually apply that particular model or that particular template to all of our data sets and convert all of the values to z-score. Then, instead of having a scale of 1 to 10 and a scale of 1 to 100 that can mess us up, we're going to have two scales that run anywhere from -3 to 3, and they'll both be the same. You just basically be calculating the distance from the mean. All right, choosing K. How do we know what K should be? If K is 1, then we're only going to find the single nearest record. And we're basically going to say, all right, you found the closest record using Euclidean distance after we've converted or normalized. Then we run the Euclidean distance algorithm, or the distance metric, and then we find the record that's closest, and we just take the record to be classified. It just takes the attributes of the record that is closest. It just assumes that class, and that's fine. But the problem is that there may be problems with that as far as noise. And what I mean by noise is that you're not going to get a very stable model if you're only looking at one record. So what we might do instead is we might look at more records. In this case, they've got an example where they're looking at 5, and we're going to find the 5 closest records. Okay? If we find the 5 closest records and they're all of the same class, that's pretty good. That tells us that the record that we're looking at is probably pretty similar to those 5 closest records. That doesn't always happen, though. In a case where we find the 5 closest records, we might find 3 of them are of class A and 2 of them are of class B. And again, the majority rules. So the record to be classified would take on the attribute of class A. Like I said earlier, there are entire algorithms, and the book goes into one example of how you can use sort of a method to determine what your K should be. I'm not going to drill into the weeds that much because I think that's getting into too much detail. I really just want you guys to get an understanding of what kNN classifier is all about without having to worry about this whole large complex process of selecting K. So anyway, we will choose the K which typically has the lowest error rate in the validation data. That's, again, getting into the weeds a little bit. We'll go through a process of actually validating a classification. That's your assignment actually this week, but we won't worry about the determination of K at this point. But if you have low values of K, you can capture local structure in the data, but you can also capture noise. What that basically means is you're not looking at enough examples of records to really make a full and complete classification. You might find one record or three records that look very similar to the record you want to classify, but you may not be looking at enough data to actually really make a full determination of what that class should really be. If you pick large numbers of K, then you're going to probably have a better chance of being able to sort of determine the right class that it should go into. But that brings problems too, because you may mask relationships, very tight or very small relationships that are actually significant in comparing K or comparing your records to your existing records. All right, we have an example that we're going to run through. It's writing mowers. This is a really small data set. And what we're trying to determine is of the 24 households that are classified, there are two variables that we're worried about. One is income and the other one's lot size. Okay, so when we have income and lot size, can we determine whether or not that particular household is likely to own a riding lawnmower? So our predictors become income and lot size, and we'll run it through a kNN classification process, and we'll determine for 4 new records, 4 new customers. We know their income, we know their lot size, but we don't really know whether or not they own a riding mower or they don't own a riding mower. And based on the information we have in our data set, can we determine the likelihood of them actually being an owner or a non-owner of a riding lawnmower? Here's our data set, and you've got pretty even split between owners and non-owners. And we'll go into this much more into when we go through the script. And to wrap up, the advantages of kNN clustering. It is simple. There's really no assumptions required about normal distribution. The data can be all over the place. And it is effective at capturing complex interactions amongst variables without having to define a statistical model. Again, it just looks at the data. It doesn't actually build a model. It just looks at the data. Shortcomings, however, required size of training set increases exponentially with the number of predictors. So if we have more than 2 predictors, then typically we'll need to have a much larger data set. In a large training set, it takes a long time to find distances. That's because Euclidean distance is kind of a hog, because you've got to calculate the distance between every one of your records to be classified and every one of your records that have already been classified. So imagine you had a training set of 10,000 records. You'd be making 10,000 Euclidean distance calculations for every record that you wanted to classify. That's kind of a drag. And these constitute the curse of dimensionality, meaning that your data set just becomes too big. So you might want to pare it down a bit. All right, summary. Find distance between records to be classified and all other records. So that's what we're doing in Euclidean distance. And that's what we're doing actually in kNN. And then we're going to select the k nearest records, and we're going to classify based on the majority, right? Typically, we will select odd numbers of records because then we will always have a majority. You can also use the kNN classifier for predicting values. We didn't talk about that at all, but if you wanted to, you could use the Euclidean distance process to determine k nearest neighbors, whether it be 5, 10, or whatever. And then instead of classifying a record as Class A, Class B, Class C, you could take the values of those 10, 5, 10, whatever records, take the mean of those, and that takes on now the value of what your new records could be. So imagine instead of looking at owner versus non-owner, we're looking at some continuous numerical value, and we want to try to calculate what that's likely to be based on our other data sets. So we can do similar to what we did for linear regression. We could calculate a mean of the k nearest records, and that becomes the new value in our newly classified records. Okay, what I'm going to do next is I'm going to go through the script, and I'm going to show you how we can run this process. It's actually pretty easy. It's really the setup that takes most of the time, but the actual kNN classification is pretty simple. So we'll go through that next.